Today, we're diving into a fascinating investigation, following a team of researchers as they put a massive promise from the world of AI to the test. And this is a promise that, if it were true, could literally change everything from weather forecasting to engineering. So let's see what they found.
At the heart of all this is a really powerful idea: AI super-resolution. And the question behind it sounds almost like science fiction, right? Can you really train an AI model on blurry, low-resolution data and have it magically generate the sharp, high-definition version, even with details it has never ever seen before? And here's why this is such a huge deal. Simulating complex physics, like weather patterns or the way air flows over a wing, is incredibly expensive and takes a ton of computing power. The dream was to just train an AI on the cheap, low-resolution data and then have it predict the outcome in stunning, high-res detail. I mean, think of the time and money that could save.
Now, the fancy technical term for this dream is zero-shot super-resolution. The idea is that this special kind of AI, called a machine-learned operator, or MLO, could be trained once at a low resolution. And then, and this is the key part, with zero extra training, it could accurately spit out predictions at any higher resolution you wanted.
So let's just take a moment to really soak in how big of a promise this really was.
If this actually worked, it wouldn't just be some neat little trick. We are talking about a genuine game changer. Imagine creating more accurate climate models, designing more efficient airplanes, or running incredibly complex engineering simulations, all by training an AI on data that's just a fraction of the cost to produce. The stakes here were absolutely massive.
But you know how it goes. Big promises demand big proof. And that's exactly what this team of researchers decided to do. They decided to put it to the test.
So, in their own words, they set out to rigorously test this claim. They weren't just going to take the hype at face value, they were putting this supposed innovation on trial to see if it could actually hold up under pressure.
They broke the problem down into two key challenges. First, there's interpolation. Think of it like connecting the dots. If the model has seen the basic shape of something, can it fill in the gaps smoothly? But the real test, the holy grail, was extrapolation. Could the model actually draw new dots? Could it predict fine details and high-frequency information that simply didn't exist in its blurry training data?
So they ran the tests, the AI models got to work. And, well, this is where our story takes a pretty dramatic turn.
The verdict came in, and it was not good. The models failed. And they didn't just fail a little bit. They failed spectacularly. They were not only inaccurate, but they started producing these bizarre, glitchy visual errors that weren't in the original data at all. The promise was starting to completely unravel. And this visual illustrates the problem perfectly. On one side, you've got the ground truth, what the simulation is supposed to look like, all clean and accurate. And on the other side, you have the AI's prediction. Just look at those weird lines and patterns. The paper calls them striation artifacts. The AI wasn't just failing to see in high def, it was literally hallucinating. The culprit behind all this actually has a name: aliasing. So here's what was happening. When the model tried to guess at those high-frequency details it had never seen, it got totally confused. It's kind of like when you hear static on the radio and your brain tries to turn it into a song. The AI was misinterpreting things and creating these ugly, noisy patterns where there should have been crisp, clean detail.
This chart here makes it crystal clear. The ground truth data, as you can see, has very little energy or information in that high frequency range. But now, look at the model's prediction. Whoa, there's a massive spike. The AI is literally just inventing high frequency noise that doesn't exist, which confirms it was just making things up.
So the initial promise was officially broken. But the story doesn't end there. The researchers then decided to investigate a couple of popular ideas that were floating around as potential fixes for this problem.
Okay, so the first idea sounds incredibly smart, right? If you're modeling fluid dynamics, why not just, bake the actual laws of physics directly into the AI's training? Force it to create outputs that follow the rules. Sounds like a perfect solution, doesn't it?
Well, here's the twist you probably didn't see coming. As this chart shows, adding those physics constraints actually made the models perform worse. The error rate went up. It turns out, forcing the model to follow these strict rules actually made it even harder for it to learn. It was a complete dead end.
All right, so idea number 1, crash and burned. What about idea number 2? This one also sounds pretty clever. It's called band-limited learning, and the logic is simple. If the high frequencies are causing all the glitches and noise,
Why not just tell the model to ignore them? Just focus on the stuff it was trained on.
And this approach did get rid of the ugly artifacts. That's the good news. The bad news? In doing so, it completely gave up on the entire goal of super resolution. The model was no longer hallucinating noise, but it also wasn't predicting any fine details at all. It basically solved the problem by refusing to do the job. So yeah, another dead end.
So, after showing that these two popular fixes just didn't work, the researchers proposed their own solution. And its real beauty lies in just how simple and pragmatic it is.
They called it multi-resolution training. And the core idea is, well, it's almost embarrassingly obvious in hindsight. If you want an AI to be good at understanding multiple resolutions, you should probably, show it multiple resolutions during training. It's not some magic trick, it's just really solid, good old-fashioned data science.
And here's the best part. It's also incredibly efficient. You don't need tons of that expensive, hard-to-get high-resolution data. The researchers found that you can train the AI mostly on the cheap, low-res stuff and then just add a small sprinkle of higher-res examples. And that little mix is enough to get the job done.
And this table really sums it all up beautifully. That zero-shot approach, it was brittle, unreliable, and ultimately a false promise. But multi-resolution training, it's robust, it's accurate, and it's highly efficient. It's a practical solution that actually works in the real world.
So what's the big takeaway from all this? This story isn't just about one algorithm. It's a powerful reminder that in this fast-moving, hype-filled world of AI, real progress doesn't come from flashy promises. It comes from rigorous testing and building pragmatic solutions that are proven to work.
And that leaves us with one final thought to chew on. As the promises of AI get bigger and bolder every single day, this research really shows us how important it is to keep asking the right questions. How can all of us, as we navigate this new world, get better at separating the genuine breakthroughs from the inevitable hype?